everyone. We are the Lady Lion Steamers. My name is Emily.
My name is Alina.
I'm Yi.
I'm Quinn.
I'm Rachel.
And I'm Vicky.
And this is our design review.
To start, we will go over our SMART requirements. SMART is a mnemonic acronym which gives a guide and criteria in setting of objectives. SMART stands for specific, measurable, attainable, relevant, and time-based. To start, we have the S in SMART, which stands for specific. Here, we set well-defined and clear objectives for our CubeSat. Our few objectives that we have is that our CubeSat will relay images to the MIT ground receiver, and then different components of the CubeSat will require different voltage levels and draw varying amounts of current. Lastly, our CubeSat camera will be able to detect colored plastic in the ocean from space with the OpenCV Python library. Next up, we have the M in SMART, which is measurable, where we provide specific criteria that measures our progress towards our goal. Our objective here is to add at least 2 L brackets on each of the CubeSat to accommodate acceleration loads, as well as have a power bank that is below a certain weight to prevent any extra weight. Our CubeSat should also be able to draw 11.5 watts of power. Moving on, we have A in SMART, which is attainable, where we have achievable objectives. Here, we want our CubeSat software to accept remote updates through the communication links and leave empty space for air to vent into area of low pressure, which will prevent any further damage, as well as be able to verify the camera payload lens is not covered in deposits of outgas material, which can lead to images that are not usable. Next, we have the R in SMART, which is where we present relevant and realistic objectives, which here we want our CubeSat to be able to operate in low Earth orbit, which we will need an orbital perturbation model to determine why the CubeSat's orbit differs from the ideal orbit. We also expect to have an optimal amount of sunlight for a fully charged battery and much power. Lastly, we have our time-based requirement, which is the T in SMART, where we present objectives that include a time frame. Here, our goal is that our CubeSat will take a picture every 5 seconds and will also commit IMU data to GitHub every 5 seconds as well. Lastly, the battery of our CubeSat should have around 10 to 80 watts per hour.
Next is the concept of operations. So for the concept of operations, I'll be discussing how the CubeSat functions. First, the CubeSat is launched into space and deployed into low Earth orbit. Once in orbit, the CubeSat battery will be charged via a solar panel to power the system. Then, the CubeSat will be oriented to point at the ground target, which is the colored plastic, based off of the IMU or the gyroscope data, and will obtain image of the target. And lastly, the CubeSat will relay images of the colored plastic to MIT ground station receiver via Bluetooth. So our goal for our CubeSat is to detect colored plastic by taking pictures with our camera and using our OpenCV code to identify the plastic. Our integration and test plan does go off of our concept of operations, but to add more onto it, we obviously cannot send this CubeSat to space, so we're going to lay pieces of colored plastic on the floor and stimulate an orbit by spinning around in a circle for about 10 minutes, just as our partner Rachel is doing on the right side of this GIF, with pictures being taken every 5 seconds of it to see if it is able to detect the colored plastic.
Okay, so I was in charge of the CAD for our CubeSat along with our block diagram. Let's start off with our block diagram. We first begin with our solar panel, which charges the power bank, and they are connected through a USB-A to USB-C cable. From there, we use the USB-A to USB-C cable from the power bank to power the Raspberry Pi. The Raspberry Pi is connected to the IMU through jumper cables. The IMU is essentially a gyroscope giving us data on acceleration, angular velocity, and temperature. The Raspberry Pi is also connected through a ribbon cable to a Raspberry Pi camera module that will be taking our pictures, which will be processed to look for colored plastic. Let's move on to the CAD portion now. Although our cubes had already been assembled, we thought it was important to still CAD it to not only learn how to CAD, but also have a more mobile, accurate representation of our CubeSat's layout. We used more than just the supplies MIT gave us. For the structure, we did use the acrylic panels and their screws and hex nuts, but we scrapped free polycarbonate from our first robotic team's robots broken intake and decided to use it to hold up our power bank since we felt acrylic paneling couldn't handle the weight very well. Seeing the holes available in the middle of the acrylic, we decided to utilize these to make a shelf using L-brackets and polycarb, which, like I mentioned before, holds up the battery. Also, in order for the battery to stay on the polycarb, we velcroed the battery in the polycarb. We stabilized the structure of the cube by screwing corner rails to the acrylic side panels, which are placed at the top and bottom of each acrylic panel. At the bottom, we have our Raspberry Pi with a camera at the CubeSat's base and the connected IMU. The solar panel sits at the top, with it being the only thing outside of the safety of the acrylic paneling. And here are some of the pictures of our CubeSat.
Next, we have software architecture. The image shows the order which I'll be talking about. Since the image is too small, I'll be talking about each box separately. First, our CubeSat has 3 components: solar panel, power bank, and Raspberry Pi. What the solar panel does is that it powers the power bank, which will then power the Raspberry Pi. This process enables the Raspberry Pi to take pictures and rotate based off the IMU's data, where it classifies if it sees colored plastic with the taken pictures. Well, how does the CubeSat take those pictures? We would need to code its function and using Python. Git or GitHub will then organize it and download it into the OpenCV library. An OpenCV library is a tool that allows us to identify and process specific images or objects. So in this case, it will process and detect the colored plastics using the Python code. This will lead to the 3 different modes that will enable this detection. The imaging mode will take pictures of the plastic in the ocean and transmit it to the analysis mode, where it analyzes and processes the images. Once the analysis is complete, it will transmit to COM mode, where the data would be downlinked to Earth. Basically, the CubeSat's transmitter will modulate and amplify the data. Then the CubeSat's transmit antenna will radiate the signal through a channel, reaching the ground station antenna, which is on Earth. The ground station antenna will then amplify the signal through a low noise amplifier and demodulate it to get back the received data. Once the data is received, it is sent to the people who will be using or need the CubeSat. So scientists and ocean cleanup organizations, where they can locate the plastic from the received data and collect the plastics found or research on the effects of the plastics.
So next is the link budget. There's a lot of data, so to summarize, the uplink transmitter sends data signals from the ground station to the CubeSat in space. So first we found the uplink equivalent isotropic radiated power, or the EIRP, to estimate the output power. And next is the channel. The channel is where signals flow between the ground station and the CubeSat. It's to find how much strength that the signal was lost while traveling to the CubeSat. We calculated the free space path lost. Then we found the uplink received power, which is when the signals have reached the CubeSat and how much power the CubeSat receives. On the next slide, we calculate the signal to noise ratio, which is a measurement of the strength of the signal to the background noise. And lastly is the downlink budget, which includes the calculations for when the satellite sends back data signals to the ground station.
Okay, so let's jump straight into the power budget. So this is the calculated power per mode. So let's start off with science mode, which obviously takes the most amount of power based off of this graph. So the science mode includes the power needed to not only power the camera and the Raspberry Pi, but also to take pictures, as well as power the IMU or gyroscope to give us data on acceleration and angular velocity. So to do so, how I did this is I ran the FlatSat code so the Raspberry Pi would take pictures every 10 seconds and upload it to GitHub. And so every 10 seconds, I would take a picture of the voltmeter and the current. And at the end of the 10 minutes, I would total up all the currents and convert it into watts. And so I did something similar for the IMU or gyroscope. where I spun around for 10 minutes with every 10 seconds taking a picture of the current and similarly totaling it and converting it to watts. The calm mode is just the Bluetooth between the Raspberry Pi and my phone, and I would total the currents every 10 seconds in the total 10 minutes. And lastly, we have idle mode, which I thought meant the CubeSat wasn't doing anything, so it was only being powered. And so again, I took the currents every 10 seconds during the 10 minutes and totaled it all up. So when you add all the power needed for each mode, we get a total of 11.5 watts needed for the entire CubeSat. So let's continue with the power subsystem. I graphed the battery percentage over time with it starting at 100%, and then at the end of the 10 minutes or 600 seconds, it was 98%.
Okay, so now we have the mass budget, which is essentially a measurement in total of how much each item that we use in the CubeSat weighs. The communication subsystem is where the ground antenna and the CubeSat communicate by sending data signals back and forth. This subsystem includes the Raspberry Pi, the Raspberry Pi power supply, the micro SD card, the Raspberry Pi camera, the Raspberry Pi camera case, and the IMU. And then the power system is where the battery uses solar energy to power the CubeSat, and which includes basically three things: the battery, the right angle USB cable, and the solar panel assembly. And then finally, we have structure, which is the construction information of our CubeSat. And the materials we use to build the structure of this CubeSat are the acrylic panels and side brackets, aluminum corner rails, an SD card reader, panhead screws, hex nuts, nylon standoffs, and jumper wires. And then this is the materials. This is basically how much everything costs and the quantity of each material that was used. Using the subsystems mentioned before, that we categorized these systems and we priced them. This CubeSat in total costs $269.93. Wait, $269.93, and then we used 135 items in total.
Okay, so let's get into the data budget. So the only data that our team can really think of that we need for the CubeSat is going to be the IMU and gyroscope data, along with the pictures needed where we can process it with the OpenCV code to see if we can detect any colored plastic. But let's start with the data budget for the IMU or gyroscope data. So how I calculated the IMU or gyroscope's total kilobytes is I uploaded code to the Raspberry Pi that would take data from the IMU and commit this data to GitHub in a .txt file every 5 seconds, as you can see in this picture. After the 10 minutes, I looked at the final kilobytes of the .txt file, which was only 13.7 kilobytes. And so the graph on the right just demonstrates the growth of the data is linear over time. Let's move into the second part of the data budget. This is going to be for the pictures. So obviously the pictures are going to take up a lot more data than the IMU or gyroscope data. Over 600 seconds, at the end, it totals almost close to 50,000 kilobytes. So this is just a total of both of them. Again, the pictures specifically were 49,200 kilobytes. The gyroscope or IMU data took 13.7 kilobytes. And for the total, it was around 49,300 kilobytes. That's the end of our presentation. Thank you so much for watching.